So now I have finished the presentation of the Bayesian procedures. So we look at the certainty equivalent Bayesian asset allocation methodologies, then the Black-Litterman, that is also Bayesian. Now we have other methodologies more in the line of robust methodologies. And the resampling methodology is the first one. Resample methodology was developed by Michaud. Here it's just for you to know that it's a patent. So when we use it in practice, you cannot say that you are using resampled asset allocation, because the name resampled asset allocation is from Michaud. And you need to pay for that. And there are some assumptions for the methodology, but instead of read all the assumptions there, I'm going to present the procedure, and then looking at the procedure, we are going to note the assumptions behind it. So there is the original resampled is also included in the material. I'm going to present a generic one, okay? So there is some interference here. Unlike the Bayesian and Black-Litterman approach, where the estimates of the input parameters are smoothed, in this case, in the resampled methodology, we smooth the outputs. So that's the basic idea behind the resampled asset allocation from Michaud. So generalized resampled asset allocation. So the procedure is to obtain the resampled allocation following the steps there. So first we estimate the market parameters. So you consider some kind of model for the market invariant. So you have an observed sequence of market invariants there, the I of t. Then after estimating the market parameters for that, you generate several sequences of observations of market invariants. And for each observation, you estimate the market parameters. So in this case, we are again considering the sequence of market invariant as a random variable. So for each realization, we have an estimation for theta. So theta hat j, so several ones. And then for each one, we solve an optimization problem. So it's a very simple procedure. So first, you have a model for the market, and then you generate, using Monte Carlo simulation, sequences. For each sequence, you estimate the model parameters, and for the parameters there you just solve the optimization problem. And solving that, you have several solutions. And now, with the several solutions, you just average the solutions and get the final one. So there are some problems with this approach. Sometimes, depending on the constraints you have in the optimization problem, you are going to have problems. It will violate the constraint. So if the constraint is very simple, for example, if the sum of the weights or the amount you allocate is equal to a certain amount or is 100%, you cannot leverage, etc., there is no problem. But if you have other kind of restrictions using linear combinations of the assets there, you are going to have problem because we are averaging the resulting allocations. But as I mentioned during the initial presentation, use MATLAB, we have several portfolios there in the efficient frontier. And when I clicked in one and then I changed it to another one, you noticed a change in the allocation. And the change is not very smooth. Sometimes the change is very drastic. So that's the problem that the methodology here is addressing, because making the average at the end of the procedure makes the allocation more smooth. And if you have uncertainty in the input parameters, the resulting allocation will not change very much along the time. So you don't need to rebalance the portfolio if something changes a little bit. Otherwise, it would be necessary to do that. And it will incur in transaction costs. So just summarizing things, we have the observer data, and then something that the parameters you obtain estimated from the observer data. Then using the parameters and the model behind that, you generate sequences of market invariants, and for each sequence, you estimate the parameters, and using the parameters, you solve the optimization problem, you obtain an allocation, and then just calculate the average of the allocations, and the QRS is the resampled asset allocation. Okay, so and just writing in a compact format, the generalized resampled allocation is given by the expected value of the quantity vector here that depends on the theta hat and is a function of the random variable of the sequence of market invariants. Okay. So it's an approach very criticized because theoretically it has some problems, but in practice people use the methodology because it works very well. So here is just an example. So you can just set some priors for the market parameters here. So again, the normal for me and a Wishart distribution for sigma hat, and then you have an expression for the allocation. And if you are using the resampled asset allocation, you can now generate sequences of market invariants, then estimate the parameters, optimize, obtain the solution here, and then you just average the solutions. And in this case, in this very simple case example, it is necessary to do it numerically. It's not possible to do that analytically. So again, obviously, it's not possible to calculate analytically the previous expectation. So it's necessary to do Monte Carlo simulation, and it's a simulation that it can take a lot of time because not only the process of generating the random numbers, but the optimizations involved. So that's the idea of the resampled asset allocation. Yeah. 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 Yes. And this approach, as I mentioned, presents several problems because you will violate some constraints doing that, because after average the solutions, you need to verify if it's okay or not. And sometimes it's not, so it's a problem. So just some points, some important points. So intuitively, the resampled asset allocation reduces the sensitivity to market parameters. That's good, giving rise to a less dispersed opportunity cost than the sample-based asset allocation. The resampled asset allocation can give rise to allocations that violate the investment constraints, and it's hard to stress test the performance of the resampled asset allocation due to the excessive computational burden. But in practice, is a procedure that I like very much because in the next, I'm going to present some robust approach, and they are good, but sometimes it's difficult to define what is called uncertainty set. So just making the resample, make it the procedure more robust, and it's very simple. So here we have what is called robust asset allocation. And robust asset allocation, the optimization problem is a min-max optimization problem. So it's a very complicated optimization problem, usually gives problems. Here we have the satisfaction function of an optimal solution minus the satisfaction function of Q that belongs to some constraint set, and it will change because here we are trying to maximize, get the worst case here inside for all the possible values for theta, and then for the worst case you get the one that is less worse. So you choose the allocation that minimize the quantity. So if the set capital theta here is very large, the allocation will not be good. Okay, so the allocation here and here, just a notation. It's important to notice that here we have a theta and here is capital theta. Okay, so the allocation Q of capital theta and its quality depends on the choice for the uncertainty sets. So small uncertainty sets is better. Then of course you can define an uncertainty set using the historical information. So it's just a notation to show that I'm here we are using historical information. And an example. So here again the linear returns and it's normal with me and the sigma, and the points here is just to indicate that here are the true expected values and covariance matrix. The uncertainty set here is defined using Mahalanobis distance, the square Mahalanobis distance. Actually here we have an ellipsoid. Here is the quantile function with a chi-square distribution with n degrees of freedom, and the p is the level of confidence. So this is an example used of uncertainty set. Here's just the definition of the Mahalanobis distance. And the probability that the real parameter, is inside the uncertainty set is equal to P. P used here. Okay. So now, just trying to extend a little bit more, I need to define some dispersion parameters. So we have, for example, covariance matrix based dispersion parameters of the posterior distribution, or of is F capital theta, or we can use the modal dispersion based dispersion parameter of the posterior distribution. Okay. So using that, it's possible to write what is called robust Bayesian asset allocation problem. And in this case, we have the uncertainty set. The uncertainty set will depend not only on the historical data, but also it will depend on some private information I'm going to insert there inside the model. And the remaining of the model is similar. So you just get the worst case here for all the thetas, and then you try to find an allocation that minimizes this worst case. Here, the definition of the uncertainty sets, again, is an ellipsoid here. So here I have an example, but it's a specific one using the mean variance framework. So the mean variance I'm minimizing here is the expected value, so it's the worst case, and then I maximize to find the allocation. And we have a constraint set and a restriction related to the level of risk that's necessary just to avoid resulting in a very risky portfolio. And then with some assumptions, it's possible to present some expressions. So here we are considering linear returns. Again, normal, given me and sigma. Me is normal, and the inverse of the covariance matrix is Wishart distribution. The private information is me0, sigma0, t0, and me0. The public information is the sample-based estimators here. So me hat, sigma hat, and t. And the expressions for the uncertainty set for me and for sigma are here. Here there is also a typo, because this one is a variation of sigma, okay, the symbol here, but it's wrong to write that it depends on me and here it depends on sigma. It's a constant there, okay. It will not change, because here you see the uncertainty set is given by a set of me, and the me is here. That's not true. It's it's actually this one is fixed for this set. Okay, so there is a typo there. And in the faded slides, I have the expressions there, so you can take a look after if you want, with the development, etc. Okay, so in terms of traditional asset allocation methodologies, you have the basic mean variance framework, the satisfaction functions there, the goal functions, the link with the utility function. We have the Bayesian approach, the robust approach, the resample approach. Now we are going to change the paradigm here and look at other kind of allocations. So now the focus is diversification. So if it's possible, for example, if you have the portfolio risk, when you increase the number of stocks, it decreases the portfolio risk. Of course, it's not possible to eliminate all the risk, but it's possible to reduce the unsystematic part of the risk using the idea of diversification. But the concept of diversification depends on the literature you use, the paper. So it's something we are going to try to organize here and try to see what is possible to do and the approach we have in practice. So there are some asset allocation methodologies using entropy measures, divergence to ensure diversification. And diversification is a risk management approach. So it's something interesting because the previous approach, the problem was portfolio management problem. And the risk management is a problem of another area. It's something that people in the market usually say, I work with management of portfolios and there is a risk area and the risk area is responsible for monitoring that and giving me reports. So that's not exactly true nowadays. It's necessary to do something integrated. So the portfolio management part together with risk management. And another point to consider is that entropy is an accepted measure of diversity. And of course, greater the level of entropy, higher the degree of portfolio diversification. So the idea of diversification is to avoid putting all the eggs in the same basket. Okay? And depending on the way you have your allocation problem, diversification looks different. So for example, in traditional asset allocation, there are a lot of portfolios in the markets that do the 40-60. 40-60 is 40% in bonds, fixed income, and 60% in stocks. But if you take a look at the risk behind that, the risk of the bonds is very low and the risk of the stocks is very high. So the contribution of the bonds to the total risk of the portfolio is small and the contribution of the risk of the stocks is high. So in this case, okay, it seems to be more or less balanced, equilibrated, but if you look at the risk allocation, it's not. So one idea is to diversify in terms of risk. And so there are asset allocation based on weights or quantities, as we use it during all the slides I explained it. And the other approach is to think about risk contribution. So the idea of diversification in weight-based methodologies is related to allocation weights. So the allocation weights ideally must be uniformly distributed. That's not really right because you have correlation between assets and only making uniformly distributed weights or equal weights for everything. It will not diversify exactly, but that's the idea. There is also another problem related to something you already know. The problem is related to the mean and variance because you need to enter with the mean and variance in the mean variance procedure, in the Markoven's mean variance to obtain the portfolios. And there are several works, and I forgot to insert here, telling that in studying the fact that perturbation in mean is worse than perturbations in the covariance matrix. So, okay, if you don't have a model to forecast covariance matrix in the future, okay, if you use historical values. It's not exactly okay, but it will not give you a lot of problems. But about the returns, the mean in the future, it's something you need to have a special model. It's what gives you difference to earn money or not in your portfolio. So if you could just eliminate the problem of forecasting means, it would be very nice. And Barry and Park introduced for asset allocation, weights-based asset allocation models, the maximization of the channel entropy and the minimization of the Kullback-Leibler divergence. Okay? So just an example, using weights, I'm not using the risk contributions. Here, here considering weights, I'm just maximizing the channel entropy here and setting some constraints. It's an approach, a possible approach. Of course, if you don't have any constraint, you are going to have equal weights here. And if you have some prior allocation, or in practice, what we have is a portfolio, is a standard one. For example, when the asset allocation house is very big, we have a basic portfolio, and then the different portfolio managers just tilt it a little bit, changes it a little bit depending on something more tactical there, a short-term allocation. So if you have an allocation Q, an allocation, and Q here is not a quantity vector, Q is relative weights, and W is the variable you would like to obtain. So you have some prior information. You don't want to be very far from the Q allocation, okay? And you can set the restrictions you want and solve the optimization problem there. Now, a totally different approach are the risk-based approach. So here is just an example. It's small. I don't know if you can read, but I'm going to explain to you. Here we have accumulated returns for stocks in green. It seems to be green. And we have for treasury bills. Treasury bills, of course, the risk is very low and the return is also low. The stocks has a high volatility, a higher volatility compared with the other. Here, you have two different, have a bonds. Bonds, when I say bonds, is private, is bonds from firms, for example. So they are a little bit more risky than the treasury bills. And then you have the all seasons, is the name of a fund, a mutual fund. A hedge fund. And the Riskparity strategy is a theoretical strategy. And the all seasons is a real fund that implements Riskparity. And you see that the volatility of all seasons and the Riskparity is low. And the return achieved is quite similar to the one obtained using a portfolio of stocks. So considering the Sharpe ratio as a satisfaction measure, here, the investor will be more satisfied with all season and Riskparity compared with the stocks, even if at the end the return is the same because of the volatility. So so here is just an observation telling that Meucci introduced the use of maximization of the ring entropy as part of a leverage constraint optimization problem to achieve the Riskparity, to obtain the Riskparity allocations. So Riskparity is just a portfolio where the risk contributions of each asset class will be, we're going to try to make it equal. And intuitively, if you think about that, we are not considering, because we are just considering risk allocation, risk contribution to the total portfolio risk. We are not considering here any information concerning mean, future means. Okay. So after the subprime crisis, mainly because of it, risk tolerance of investors decreased, and Riskparity just equilibrates that. So risk-based allocation methodologies are very popular now, even here in Brazil. And there are many works that are trying to study the properties of this kind of portfolios. And the risk budgeting is just a generalization of Riskparity, because sometimes you have some prior information telling you that you don't want to have an equally weighted risk-based portfolio. In this case, for example, the paper from Bruder, they allocate in several countries, and they would like, and they use a risk budget strategy, and the idea is to allocate proportional or similar to the GDP level of each country, something that makes sense. Well, as we are going to see, it will be easy here to work with factors instead of assets. So there are many recent works dealing only with factors. Actually, nowadays, the investment product is considered a factor, so the combined factor is nice. For example, ETFs, exchange tradable funds. I don't know if you know the concept. Is an investment fund that's traded in the stock exchange. You can buy it at the stock exchange, and it represents a strategy. And is a passive strategy. A simple one is a very defined one, and usually it's just a replication of a very well-known index. So you consider that a factor, and then you mix the factors, not exactly individual assets. Well, so we are going to use principal components to represent the assets in terms of uncorrelated factors. And there is the paper from the guest that they present the concept of the effective number of bets is what they consider as the objective function to be used in the optimization problem to obtain the Riskparity portfolios. So the definition of the contribution of risk, just to formalize a little bit more, so is a vector P. And in terms of factors, you get the data you have inside of R, have the returns there, and then you have a transformation, and then you have factors. And the factors, in this case, because the idea is to use principal component analysis, for example, you can use a singular value decomposition to obtain the matrix here. You have a diagonal covariance matrix. And the relative marginal contribution for uncorrelated factors. So the expression is given here. So for that, and using the definition of effective number of bets, that depends on the contribution of the factors to the total portfolio risk here. And this notation here represents the alpha norm. And here, just opening the expressions, you see that the effective number of bets actually is the log. Actually, the log of the effective number of bets is the range entropy. It's the way that Meucci defined it. So, writing the problem as a maximization of the effective number of bets, and there the inputs are in terms of uncorrelated factors, not assets directly, and with a restriction, a leverage restriction, because the weights are summing to 1. It's possible to obtain an analytical expression for the solutions. The solutions are here. There are several solutions because here, the symbol here, this I here, it's a combination of plus, minus 1, all the combinations of them. So you have multiple solutions for the Riskparity problem here. But this one is a leverage, it's not a lowered leverage. So we can generalize it, and if you just maximize the effective number of bets, the solution is given here. And it's the same one from the previous slide, but we have a lambda and lambda belongs to the real numbers. It's different from 0, of course, because we don't want a 0 allocation. And then you are going to have all the Riskparity portfolios. So just an observation telling that with the modification, this part of the presentation is part of a paper I presented in the MaxEnt last year, so I'm just repeating things. So it's possible to achieve any risk level. Because using Riskparity, the problem is that you only enter with risk inside of the model, the covariance matrix there. You don't use any information about the mean. But even so, you need to take care because you have different profiles, investor profiles, and you need to adjust the level of the risk you have in the portfolio. And just to finish here, we have the factor risk budgeting problem. So the risk budgeting problem considering factors is the factor risk budgeting. And the optimization problem is given here, and here D alpha is the range E divergence, or R alpha divergence, given here, the expression. So if you minimize that, it's possible to obtain analytical solutions. And the analytical solutions are given here, are quite similar to the ones obtained for Riskparity portfolios, but here you have some prior information. For example, the GDP of each country if the allocation is between different countries. Okay, and that's it. So the idea of the tutorial was to give you an overview of what we have in terms of methodologies, and what we have, and some at the end, the risk-based methodologies are something new, so I just included as an additional thing, but we didn't mention anything about models for expected values. So in practice, okay, I have my asset allocation model, the optimization problem there, but I need to generate the inputs to insert. Sometimes I have a committee, I don't have, but another area has a committee, and they have some beliefs, and it's possible to combine the beliefs with information from the market. But in my case, I have models for expected values. And I have, of course, backtests and some models of the nature there to generate trajectories to test the strategy. So since I have the history of it, it's possible to calculate the uncertainty of the strategy and insert inside the optimization problem. One problem that arises at this point is when you have several strategies, and asset allocation methodologies for strategies is something different. Okay, so usually it won't work very well if you just apply the methodologies I have shown here to allocate between strategies. One problem is very simple to understand, is that if you allocate considering the results of the strategies, usually you are going to allocate in the strategies that are giving more money. But if the strategy is in your portfolio, the reason is that you believe the strategy will deliver money. So if it's not delivering money, it will deliver in some future horizon. So if you just decrease the allocation because of it, it will be really a problem. So the allocation methodology must consider that fact. Well, so again, the covariance matrix is also something the models for that we didn't consider here, but something people like to use nowadays is the, I don't know if you know the GARCH model. So there is the dynamic correlation, conditional correlation model is a generalization of the GARCH to obtain covariance matrix. So it's something that we can use, and it changes a lot like the GARCH model. So it's possible to react very quickly to the market. And also, we didn't consider anything about transaction costs. There is also the problem of asset liability management models. Here, I'm just trying to obtain, in terms of absolute value, the better portfolio. But if you have some liabilities, some passive, so it's necessary to match them. So have a cash flow matching problem together with the optimization problem of the mean variance optimization problem. So usually institutional investors, they have this kind of problem, pension funds, because they have benefits to be paid in the future, and they need to match the flows. Nowadays, there is something that actually, with the automation of things, people are discussing what is called robo-advisor. I don't know if you heard about that. Usually are services that people, not the institutions or pension funds, just put there the flows you have, and then it will create an allocation that will consider your liabilities, your passive, something you would like to desire to do in the future. For example, if you say, okay, I received this amount of money each month, I have this amount already invested, and I also have the desire to buy a car or to travel or to buy a house, and then I put there, I insert there with the time horizons there, and then it's necessary to solve a different optimization problem. There is a paper from Martellini, a very recent one, that calls the procedure goal-based investment. Another point that we didn't address here is the multiple asset class allocation problem. So here we just considered equities, but if you consider derivatives, we need to change some details. And the multiple period asset allocation is also something we didn't address it here. We just considered a time horizontal, but if you have a multiple period asset allocation, you need to have models not only for the expected value in the future in a certain time horizon, but need to generate all the trajectories of prices in the futures together with the correlations to do the optimization. Okay? So it becomes like a stochastic control problem. It's something that is very interesting that we also do. So that's it. So